Okay, so today in this consciousness trialogue, I'm very happy to have both Hayato and so Alex to talk about, in a sense, relevance of mathematics in understanding consciousness, in a sense. And so just briefly to explain, to introduce, Hayato has been, and he's the master, I mean, my master, at least, of the category theory. He inspired me in various domain. And recently, I also found that what you said pretty much along all the years is pretty much consistent with what is the book that we are going to talk about today, The Joy of Abstract Thinking. Joy of Abstraction, I think, by Eugenia
Cheng.
Cheng.
Eugenia Cheng. Cheng.
Do you know him? Do you know her?
Not in person, but I know about her because
Right.
he is a very brilliant categorist.
Right. And this is a book that Alex recommended me last week after we finished the recording this, this YouTube session, and I was pretty impressed by how much you learned about math. But also, I thought that it would be really great to have a mathematician's perspective on this kind of discussion. So that's the reason why I thought that's great to have this session today. And Alex has been also, initially been a neuroscientist, a psychologist to study consciousness, but recently, kind of took the turn to focus more on this mathematical approach to consciousness. So it's great to have your perspective about this. And maybe, Hayato, you may be able to, or I don't know which one you guys want to start talking about, but in general, do you have any comment about this Eugenia's Joy of Abstraction book?
I have never read this book, so
Okay.
maybe the other guys should.
Yeah, so something like, what I found, so this is the first, one of the first, figure in this book that explains that the traditional mathematics had some kind of hurdle to get from the time stable to category theory as a sort of most abstract, way of mathematics. And you don't get to, as a mathematician, for example, you don't learn category theory formally, right? And that's also what, Eugenia also explains. So pretty much, in a sense, what you have been telling me, Hayato, to has been backed up by her book. And she thinks that, it's better to think mathematics as a this way, like connected kind of areas of the fields. And category theory is one of the component, but it has an interesting kind of property here, which is that once you understand this, you actually see more of this calculus or algebra or arithmetic times table at the high level, from the high level. And I totally completely agree with this because I didn't learn like group theory or topology formally in university, but in my case, I really liked Spivak's category theory for science. And that was the inspiration for me. But in her terms, so previously, like McLean's book is super difficult and only relevant or usable, understandable by the trained mathematician, because he uses a lot of examples and also logic for the people who already learned mathematics, right?
Maybe this McLean means the category for the working mathematician,
yes.
the book. Yeah. It is very good book, I think, but as title shows, this is for the working mathematician. So working means not retired. So just for the working mathematician. So the mathematician, some mathematician works on group theory, some mathematician works on topology, measure theory, functional analysis, or something. So this book is written for some kind of demonstration of the utility and beauty of category theory for this kind of special mathematicians working special kinds of branches of mathematics. So the example is very much diverse, and I think not all or not many mathematicians can understand all the examples. So let alone the how to say the beginners of mathematics. So it's just for the working mathematician, but at least in that sense, it's very nice book. Yeah.
Yeah, and then but the program for the category theory, people who are interested in Eugenia's terms, it's a tourist mathematics where you don't necessarily need to produce the math as a mathematician, but appreciate the math or the mathematical thoughts. This one is too high as a threshold, and this was the only one existed until like year 294 or something like that, 1994. And then Rovere and Awadi and Leinster and Leo started to write more understandable book for graduate mathematics students.
I think that this Rovere Chanel book is actually written for high school students.
Right.
But it contains some very difficult topics also, and it's high level.
This is conceptual mathematics, right?
Conceptual mathematics. I think this is it on this.
Yeah, it's written in a conversational kind of style between the teacher and student, and it's quite interesting. And
I think it's very nicely written. Some kind of you can't see, but some kind of dialogue.
Yeah,
style.
Because you put the blur, we can't see.
Yes.
Blur in the Zoom. Yeah. All right. Yeah. But then, Eugenia wrote this book, How to Bake Pie, which I haven't read, but she thought that there's still a gap between here to here, and then that's this joy of abstraction. And it doesn't. What I really like about this is that it doesn't contain any questions. That problem sets, which is always required for all these mathematics books, right? And also, it's written in a way that is less mathematical kind of language. I always have a problem with in a sense it's pretentious, right? Like it's easy to generalize this into that. But as a reader, it's very difficult to see how it can be generalized to, let's say, from one-dimensional to two-dimensional. If I try to do it, I can't do it. But it's mathematical way of talking about this kind of proof, right? She doesn't do it. So I think this is very accessible and a very important kind of book for, especially that people like interested in application of a mathematical thinking, not necessarily category theory, to consciousness research.
Yeah, actually, I and my colleague wrote in Japanese this kind of book. I have never read the Joy of Abstraction, but maybe it has the same kind of role.
Yeah. But I think, I read yours as well in Japanese. Her style is also a bit different. Yeah. She can get quite, political, but it also kind of put in a feel of what's relevant in terms of, to the world. So I strongly recommend this, and I really thank Alex to introduce this to me. Have you read that, Alex, entirely, or?
I'm still in the process.
But so I'm also still in the first several chapter, like chapter 4 or something like that. But many things that we also pointed out in the previous papers, like the importance of the difference in the sameness, or difference or importance of making it clear which context we are talking about what. All of these things that already appears in the first few chapters, pointed out exactly the way we also emphasize in our paper. So that I thought that's very interesting.
Sounds interesting.
Yeah. And then so the top left is the current kind of field that use category theory to many different kind of system, and it still doesn't contain consciousness, but hopefully in the second revision or something she may include that. And then other things that I wanted to talk about this, it may be okay.
Can I ask?
Yeah.
Can I ask you quick? So if I understood correctly, you said that category theory still isn't taught, or at least not regularly at university. So I'd be curious, just really quick, how did you learn about category theory, Hayato? What got you into category theory?
For the mathematician, such a student in mathematics.
In your case, in
my case, it's I read the Japanese translation of this book, the McLean's another book, the mathematics form and function in high school years.
This one, right?
The last the 11th chapter is dedicated to the set theory, logic, and category theory or something. So 11th, I think. Yeah, 11th chapter, the second to last chapter. And I'm very interested in that chapter, but I cannot understand that chapter. And I decided to run the category theory as a first year undergraduate. But I happen to have some disease, a very a kind of not so fatal one, but I have to be hospital the half years, first half year, so the semester of the undergraduates. So I just have the books from the library about topos theory or category theory. So this semester I must learn this. So no alternatives. So I first learned category theory. Then after that, I learned calculus and linear algebra or something. So I'm very lucky in that sense. So traditional education in traditional course of mathematics, the category theory is put on the higher level, like this area. And also sometimes, for example, in my case, I was a student in Kyoto University. But in Kyoto University, there is many mathematical students, but there is no course on category theory. So category theory is some kind of what you have to learn yourself in this traditional course of mathematics, even in mathematics. But after you became graduate students, you are supposed to know that category theory. So there is no course, but you must know such kind of the mysterious position for the category theory. So for my case, it's just some kind of happening. Yes. So it is I'm living evidence of the utility of category theory in the mathematical learning.
Yeah. Sounds good. Yeah, so I think this this model is the one that we really should advertise for the people. And Eugenia actually also points out that pros and cons of going into the abstract thinking. And as a cons, she says that learning abstraction can be actually difficult or effortful at the beginning, but it's highly rewarding later. So if you, and I think, one of your edited category theory book, category theory of the how to
category
walk.
theory horizon.
Yeah. No, how to walk in the world of the category. The Kenron no arukikata.
Category theory trotters.
Yeah. Protas. Yeah. One of the persons says that category theory is something that you need to invest your effort in the beginning, but then the benefit comes later, little bit, visible and large chunk, and that's what I also feel like actually.
Yeah, I agree. But I want to stress the other aspects of this kind of things. That is, why category theory is so useful, or this is a very analogical question. Why mathematics is useful for other sciences? A very how to say analogical question. My tentative answer is it is quite resembling to category theory is quite in harmony with our primordial way of thinking. Like a 3-year-old baby child also have kind of process-like thinking or the compositional thinking, if you draw from the Bob Cook and the colleagues' term. So I think that it is, if the category theory is too abstract, then every person has this too abstract structural way of thinking. So it is too natural. So it is difficult to recognize. You know, so
like air.
Yeah. Yes. The kind of
all the time.
Yes. So you cannot explain how to walk if you can walk. But if you need to win for example, the walk competition or 競歩ってなんていうの? How to
walking.
say?
I don't know.
Walking, yeah, walking race or something. Then I think you should study this kind of how we walk or something. How should walk?
Right.
So category theory is in one aspect, it is difficult or abstract, or it must have some cognitive costs or something. But on the other hand, it is quite primitive. It is quite, how to say, in harmony with our native way of thinking or something. So it is. It seems contradict, but I think it is the very natural thing.
I think this is also kind of related to what you were saying before we started the recording, Alex, right? I guess.
Yeah, I think that what intrigues me, what really shook my world when I read your papers, is that despite the fact that it's so abstract, you already have some very concrete findings and ideas, in particular for how it's important for consciousness research. And I realized that if you limit mathematics to what is being taught on the undergraduate level in university, so that's arithmetic, some calculus, linear algebra, and you try to approach that topic with those limited tools, you would have never gotten to that point. You would have never made that progress. So for me, the two things that you wrote that really changed the way I think about it forever. One, the application of the Yoneda lemma to color vision. And the second, the idea of isomorphism, and then also adjunction, basically applying that to the mind-body problem in a way. And so that basically what it did to my thinking was, before I just thought about equations. And so I realized there's more than identity. And so so despite the fact that this seems to be so abstract, there's you already have some very concrete results, and it proves that this is a successful strategy.
Yeah,
it's also it's also interesting. It seems that it's very timely, right? So category theory, at least if you here on YouTube, it seems to explode in interest, right? So you already mentioned David Spivak and the Topos Institute and Bob Koch, and so there's this whole notion of applied category theory, and so other fields are looking into that as well and seem to make breakthroughs as well. So John Bates' work. So it's almost like it's in the air. Lots of people are thinking about compositionality in computer science. I think Haskell is inspired by that. It's a programming language. And it seems to spread quickly within science. But the most compelling results so far, I think, that I've seen with my limited view, were your works in consciousness, and particularly neuroscience of consciousness.
Thank you. I think this figure that also is kind of consistent with what you guys both are talking, right? As a level of the abstraction, once you get to the level of the composition of the two things here, A and B, and then to get something else, when the end point of A corresponds to the starting point of B, you allow this kind of thing. So that's a sort of to me, as a neuroscientist, and Alex, you are as well, this precisely is the neurons, right? Like, neuron has this kind of axons, and then that's connecting to another neuron like this. And then this neuron, which doesn't connect to anywhere, doesn't just basically exist, or it dies, or it does something really weird. I don't know whether this kind of thing happens, but the neuron works only through the connection from, in this case, actually, to roughly in an adult human, 100 to 10,000 to 1,000, inputs receiving, and then sending out roughly the same number of the outputs, 1,000 to 10,000 of outputs. And then each of this is connected in this way. And that's happening in 86 billion of, neurons inside our brain. And that's generating this, our conscious experience. So if this composition is at the level of the material, fundamental, basis of our experience, and as Hayato said, that, it's pretty natural, I think, intuitively at least, to think that this is the really most fundamental base of everything. And then the more sort of, concrete level is A and then B binary operation, and then one type of the binary operation is addition, and another type of the binary operation is a multiplication. But all of this is actually considered as a category composition here. And I think at this abstract level, we can also start to talk about life. So that's pretty interesting. And
this field is very interesting, because usual mathematicians think the addition is easier, the multiplication is a little difficult, function is more difficult, relation is more difficult, homotopy is more difficult. Life is the most difficult thing for the ordinary mathematician like me. But other people think life is more easier than homotopies or something. So yeah, the category theory. So you can you can have some feelings. If you like arithmetics, then you can proceed to the category theory from the arithmetic side, or some set theoretical side, or topological side, or something. And also, yeah, you can change. You can try to understand the category theory, the feeling of category theory from the life examples or something. Yeah.
Yeah. All right. So that's
and also just for the a kind of excuse and also some explanation. I'm happy to hear your evaluation of our work. For example, the Yoneda lemma or something. And in the usual daily language, application is very, how to say, very good term to describe our work as an application to Yoneda lemma. But in narrow technical sense, it is not a direct application of the mathematical theorem. It is rather some kind of the application on the thinking of, yeah, or perspective of Yoneda. And I think it is quite important. The usual mathematicians or the applied mathematicians tend to think the application of mathematics is some kind of application of theorem itself or something. Yeah, it is very important. But there is another important role of mathematics. That is making the way of thinking. And if you learn about Yoneda lemma, you have to change your way of thinking. You would change the drastic change on your way of thinking. So a kind of generalized kind of application of Yoneda lemma. It is more, how to say, correct description. And it has been under-evaluated in the traditional academia, I think. But for example, this is not a true application. It's just some kind of motivation or motivating something or inspiration or something, but it's not rigorous or something. But what we aim at is by using the term of category theory, you can make the broader perspective and a broader sense of broader feeling of how to proceed. So I think it is very important aspects of the mathematics. For example, Descartes, the Cartesians uses Cartesian coordinates, x, y, or something. Some people would say that only the mathematicians or physicists or such kind of scientists or engineer use the coordinates. But actually, the effects of the Cartesian evolution, Descartes' the developments of coordinates affects all aspects in modern society. I think you can use Excel because it is coordinated, or kind of. So set theoretical revolution into 20th century is quite important, and it's heavily affects our way of thinking, I think. So category theory kind of extend this kind of view to the more flexible way. And what is needed in consciousness study, for example, is this kind of a change of mind, change of the way of thinking. Yes.
Yeah, and I actually happen to probably we didn't record that, right, Alex? But last week I also wanted to discuss about this. It's great that you said, Hayato, that set theoretical revolution, and because of that we benefit a lot in the modern society. But at the same time, we are too ingrained and also too kind of restricted by the set theoretical thinking that goes really well with the classical logical thinking and also classical probability thinking. All of this is kind of connected, and it forms in its own kind of nicely coherent kind of view, but also it limits ourselves in many ways. And the particular thing that we know that it doesn't work is the quantum theory. I mean, quantum phenomena that can't be explained by this kind of idea. And at the same time, also not only consciousness, but any kind of dynamical system also can't be in general explained by this static, classical, set theoretical thinking. That's the sort of the next level of the thinking that the category theory is expected to play a role in many sort of divisions of the society. And that's the reason why I think, as Alex said, that the category theory is, kind of treated as a very useful tool to make a different kind of, appreciation about our world, how the world works.
Yeah, of course, yeah, I completely agree. For example, even in modern mathematics, mathematicians use the idea of some kind of dynamical aspects of the mathematical entities, like a arrow-like thing. But usually, it tends to be thought that this arrow should be a function, set theoretical function. It is a very traditional way of thinking. So if you try to teach category theory to the people who knows something about modern mathematics, they tends to think this arrow must be some functions in the set theoretical function, like only one input to the one output like thing. But there is more very, very how to say diverse, various candidates for this arrow-like thing. It may be indeterminate, or it may be determinate, probabilistic, quantum-like, quantum channel-like, or more and more, just a loop, okay, or some kind of, or causality relationship, or some kind of. But yeah, set theory also use the typical kind of arrow called functions, but function is very good, but not sufficient for the consciousness studies. I think you better know about that. If you stick to the input-output kind of relation, there is almost no possibilities to grasp the essence of the consciousness.
Yeah, that's a problem.
But I think this input-output kind of formulation, how to say, there's some kind of ideology, prejudice about study should be mathematically rigorous, and the mathematical rigor is just for the set theoretical rigorness or something. Then the investigation on the very, very serious investigation tend to stick to this kind of input-output kind of thing should be the most base level. This is just ideology, but strongly affected by the culture of set theoretical mathematics. I don't criticize set theory because it's very beautiful and powerful mathematical branch. Some people tend to think I attack to the set theory as a mathematics. I never attack to the set theory, but I attack to the some kind of inertia of the set theoretical thinking into the, for example, the study of the consciousness studies or something. I strongly attack that because it is good, maybe good idea, but maybe not, because there is many kind of arrows in our world. So you should choose the good arrows to study good things. Yes. So in that sense, I'm strongly advocate the importance of category theoretical way of thinking.
Right. And do you want to say something, Alex, about this?
Well, this is really interesting, and it's really cool to hear. I mean, it seems that one of the issues of the inertia may be that it has worked so well in most of science, right, to explain everything with just equations or functions. And so I think that's in consciousness we're stuck. And so that's why it's really exciting to basically be more general and open-minded. And then I think somebody who might hear it for the first time might worry that you're losing the ability to be quantitative or to compute, right? So if you don't have an input-output relationship, then can you still calculate what is going on? And so so it took me for a while to understand that, yes, you can still calculate or compute if something is isomorphic or not, for example, right?
And I think this is actually also related to this Joy of Abstraction, book that also inspired you as well, right, Alex? Most of the math taught in the school is this level: compute, calculate, and then count. This, counting, computing, calculate, see kind of, approach is the really set theoretical thing. It starts from the concrete and then applicable to things, but doesn't get to the mathematical thinking, abstraction. And yeah, so that also introduces some people's, difficulty, it seems, like to see, 1 plus 2, 2 plus 3, that's also all fine. But then why do I need to think about this, indefinite letter?
Indeterminate.
Indeterminate. And that's one of the first barrier for people who struggles with mathematics and then leave from there, right? And then
I think,
yeah,
I was about to say, I think it's even worse because I have young children and I kind of see how the standard approach to this is almost killing their natural inclination to be interested in mathematics. Because my 4-year-old, I remember for the first time when he realized that there's a concept of zero, and he's still fascinated by it. That he came to me and he said, "How can there be a number smaller than 1?" And once he got it, he loved to go to his younger brother and say, "You get 0, and that means nothing." And so there's a natural fascination that comes with it. But what we do is, yes, as you said, addition seems to be easy, and then multiplication, for whatever reason, we struggle more mentally to do it. And the way that we do it for children is that we have them learn by heart a multiplication table. So they're not doing mathematics, they're just learning something like a poem. And they have to learn it so much that they remember it for the rest of their lives. And so it's almost the opposite. We're not teaching them mathematical thought, we're just giving them the result of mathematics. And I saw another talk on YouTube where somebody said it really beautifully, and he said that we're teaching kids to compete with computers, but they're already set up to lose because computers can calculate really well. They can do calculations that humans cannot do. But what a computer cannot do is to have this mathematical kind of thought. And we should teach the children that instead. Why are we still teaching them multiplication tables if a calculator can do it as well? So I think that's why when I read Eugenia Cheng's book, that really resonated with me as well. Because I myself had the exact same problems. I didn't like mathematics. And it was by learning about your work that I realized that I thought I didn't like mathematics because I confused mathematics with multiplication tables. And I didn't realize that there's this beautiful other kind of stuff out there that we don't even learn at school.
Actually, for example, 1 plus 2 or 2 plus 3 is the product of verse abstraction itself. Itself, because number 2 is quite a huge the result of huge abstraction. So maybe 2 books, 2 drinks, 2 fingers, or this kind of all things as an isomorphism class. We recognize that too. So in that sense, isomorphism precedes numbers. In that sense. So without isomorphism notions, we can't count, even count. We lost the meaning. So in that sense, the categorical thinking is more primordial than the usual arithmetic. It is like a abstracted category. The starting point is a kind of the vague kind of notion of category. Then you can abstract as some kind of indicator. We get numbers.
I think the book also explains that this is already a one level of abstraction, right? It starts from 1 apple and 2 banana, and 1 chair and 2 tables. They are both this thing.
Yes.
And then, this is further abstracted into this. And so some kids actually get stuck on this level, right?
Yeah, it is natural. And the category theory can help them because category can treat this 1 apple and 2 bananas and 1 bananas and 2 apples or something as itself, like a kind of category of finite set you call in mathematics. So the usual arithmetics is some kind of the abstraction by thinking isomorphism as identical thing, equal. It's there is a very serious studies called higher category theory. It is just kind of how to say, the mathematics without equality. It means equality is originally some kind of isomorphism. So this is kind of category theoretical thinking. But even in category theory, there is some kind of equality between arrows, equality. So you can proceed this way of thinking. This equality between arrows, equality between 2 arrows should be higher level or deeper level of arrow. Yeah, kind of, yes, it should be some kind of isomorphism. So isomorphism. So it is a kind of the dream of children, in this higher level of category theory. 1 bananas and 2 apples is not equal to 1 apples and 2 bananas. Not equal, but that's isomorphic.
Yeah, I think this kind of alternative. So Eugenia actually talked about that this kind of approach works at least for some people to go directly here and then to see the relevance here and then come back to see this from a high level. And I think if we start seeing more people seeing the previous generation of people have been doing from a bit higher level, we will make a huge leap in terms of thinking. Especially in a sense, sort of that not only applying category theory to one particular level of the field of the science, but in fact, this life kind of stuff that this figure I really like is that the starting point is mathematical thought, right?
Yeah.
Not the category theory. And I kind of think this through this way I gain a lot about mathematical thought, and then from here to go many ways is easy.
Very, very nice description. Yeah, it is a very nice description of the merit to learn category theory.
Mm.
Mm.
And Eugene in the book says that this is based on, in a sense, logic
Mm-hmm.
and abstraction.
Mm-hmm.
And at the point that I've been reading so far, like chapter 4, she doesn't go that far. But from the kind of context that she's talking about, I think she is going to eventually say that even though mathematical thought is founded by logic and abstraction, what we mean by logic and also abstraction also depends on the context.
Mm.
Right? Like before this video, I was talking with Hayato that maybe there is different types of the logic formalism that is necessary to make progress in this consciousness research, like this exclusion of middle.
Mm-hmm.
That's pretty interesting to me, and it should happen. I mean, it should be more seriously discussing consciousness research, but I don't know whether it has been discussed. Right? We are not really, I actually was inspired by Alex. You mentioned this first time to me. So when in the neuroscience we use a random dot, the dots are moving, in a random direction. And in fact, in each frame, the X% of, let's say 50% of the dot's location is shifted to the left a little bit, but the other 50% of dots are placed in a random different new location. And if you see that movie, then it looks like it moves to the left overall. And then when you reduce this, percentage of this number of the dots that goes to the left, then it looks like kind of random. But what neuroscience really loves to do is to ask people to, choose whether it was moving to the left or right. But the qualia of seeing that is completely nothing to do with the left or right. It's more like this flickering thing, going up and down, and then that's very different kind of ambiguity from different kind of ambiguous stimulus that looks either to the left rotation or right rotation. And if you ask many people, then 50% of people to say left or 50% to say right. But that's very different kind of ambiguity. One is the ambiguity that is imposed on artificially because there is no left or right in the beginning, but are forced to say left or right. And this kind of thing, I always think that cannot be really studied with a classical logic where you have yes or no, but there has to be some kind of alternative that I don't want to say yes or no. Right.
Yeah, maybe, or undecided.
Yeah, undecided. But we usually don't learn this kind of logical system, how it works or how to deal with this. So, I'm still not really clear what to do with this, but this is one of the things that I think we need to really try to understand.
You had an interesting slide at the end that also kind of co-aligned with something that I think we talked about before that struck me when I read The History of Mathematics by Maurice Klein, where he made the point that logic was really impoverished and very poor ever since the ancient Greeks. They only knew deduction basically in this very primitive form until mathematicians basically mathematized logic. And so with Boolean algebra, what we really have in a way is the inverse. It's not that logic is applied in mathematics, but that mathematics is applied to logic. And so that is what really had logic take off, to formalize logic and to use notation for logic. And so that makes me think whether it isn't the other way around, that logic is just a product of mathematical thinking, or a child of mathematical thinking, and not the other way around. Yeah, this quote seemed to go in the same direction.
I'm starting to learn what this Peirce is was saying, and through my collaboration with Tanich-san, as
yeah, the last paragraph, the last sentence is exactly put much more eloquently than I could ever do it, but it's the same thought. And at least based on history, you could make this point, right? So that, I mean, we wouldn't even have computers if it weren't for Boolean algebra. And that is so far removed from Socrates is a man, all men are mortal, so Socrates must be mortal, which that is what logic used to be for hundreds, if not thousands of years. So in this sense, it jives with what you said, Hayato, that mathematics seems to be maybe more primordial, and the thought might be more closer to our starting point of thinking than even logic may be.
Yeah, I agree. Basically, I agree, and I would say I completely agree. But as a mathematician, I must how to say comment. It not necessarily one direction. So yeah, in general, I agree because as Peirce, I'm very fond of this Charles Sanders Peirce. He's one of the greatest guy, I think, in the history of philosophy. But Peirce interestingly orders the branch of sciences like first mathematics come, the second philosophy comes, and then physics or chemistry or something. So for Peirce, the philosophy is some kind of middle of the mathematics and the physics. Very interesting, original idea to order. This order is about the abstraction or the generality or something. So for mathematics, for Peirce, the mathematics is more abstract than philosophy and more, how to say, basic than philosophy. So logic as a branch of philosophy, yeah, I completely agree. It is based on the mathematical kind of thing. But interestingly, so mathematics include the logic. But very interestingly, if you choose logic, then you can play mathematics by this logical in how to say ingredients. Yeah, because I think it is safe to say that almost all usual mathematics can be done on the basis of first order logic, which is also related to the Peirce. Frege and Peirce developed this first order logic. Yeah, it is very good to learn this structure, to learn the broad kind of mathematics. In that sense, logic and mathematics, mathematics is broader, I think. But in the set theoretical way of thinking, then you want to say that, okay, logic is only the special kind of mathematics. So the mathematical is greater. But interestingly, in category theory, there is a notion of adjunction. Like, so some subsystem can, in a sense, grasp the total system, or this kind of include A includes B, but in a sense, B can also include A, or that kind of a very very interesting relationship. So in that sense, the logic and mathematics in general relation is interestingly modeled in the notion of topos. Topos is a kind of generalization of the set. Set is a category of sets and functions. Topos is a generalization of that. The topos set is a special kind of topos. But this topos is, how to say, the very good category in the sense that you can do the almost all mathematics in the topos, in a topos. So set is a special kind of topos. So the 20th century, the mathematics is played in the topos called set. But you can do the mathematics in the another kind of universe, so another topos. This kind of view liberates us to, how to say, the relationship of logic and mathematics. This is kind of unified or the very organically related kind of thing. So it's just a technical comment, but
I see. So just understand, in the sort of the category of the logical topos of the logic kind of thing, you may have different kind of system like here and here, and then depending on what you choose as a logical system, you can develop the entire world of the mathematics like here, and then that can be distinct if you use slightly different logical system, and then but it also falls in a kind of a related or closer kind of system within mathematics and so on, probably, right? Roughly.
Yeah. And very interestingly, topos is also related to the algebraic geometry. So topos unifies the logic and geometry and other thing, of course, computation or something. So it is, I think, which is we now and me discussed before this session, the potential role of topos in the consciousness studies. Like our brain, our consciousness has many aspects like the spatial recognition, the logical computation or something, but the relationship between them is not so clear. But if there is some kind of the evidence that our consciousness structure have a topos-like structure, then it may be some possibility to natural connection between this spatial recognition and logic or some kind of multimodal structure of the consciousness.
In cognitive science or computer science, typically these two camps are kind of fighting all the time, right? Like on one hand, it's a low-level vision, like structure, more continuous, more low-level, and spatial like. And then on the other hand, that's a more categorical, discrete, and also high-level language-like. That's a logic structure and the symbol structure. And then the history of the probably cognitive science is that which one is better kind of approach. But so what you're saying that it may be the case that the topos-like structure can naturally unify them.
Unify that. It is just a possibility, but I think it's not bad idea. And kind of, it reminds me of the William James, the philosopher. He describes some kind of two temperaments of the philosophers, the traditional, the continental and the English. Like one people tends to think that continuous is very important, discrete. The other guys uses a discrete kind of the continuous sect. Continuous sect tends to think that some kind of relationship is important. The discrete sect considers is individual is more important or something. But it is not necessary to divide these kind of things. But if you want to stress on the continuous, but you can think of the importance of individuals or the like determinism and indeterminism. You can switch these kind of thing. And I believe the middle way or the more meta level way should be considered. Yeah, I think to do this kind of investigation, the success of topos theory maybe shed light on that kind of way, but
Yeah.
it's just speculative hope.
Yeah, I think that's really, the kind of thing that I also want to do. And also, speaking of the joy of abstraction, again, she also talks about this, peculiar possibility of the category theory for going from abstract to concrete, like what we are talking about. And usually people kind of fights or sort of talk about either, concrete is more applicable and the abstract is more joyful and artistic and so on. But I found what category theory is quite promising is that it explicitly force us to realize which level we are talking about. The context, importance of the context, and also mobility across this, kind of a hierarchy or context, right? So for what particular situation, what's a good level of abstraction? And then we also realize at the same time that the one way of perspective is never complete, but we need to actually change the perspective to get a fuller view of what it is. And by going to this direction, we don't necessarily lose the resolution. That's something that I think, I was thinking this morning that the philosophical debate about the reductionism versus holism is also maybe holism versus reductionism is a strange contrast, but the argument that whether we should reduce or we can reduce or whatever they are talking about, I always feel weird. It doesn't make really sense. But the idea that we kind of consider a category, but with a possibility that inside of this category, this object can be actually also considered as another category. So you can actually magnify this. And then that has an internal structure. And then this one can also have an internal structure and so on. But we don't need to start from here. As long as we clarify that we are going to start from here, like, psychology, then we can make a very useful kind of, scientific discovery. And they don't need to form the hierarchy across the different kind of scientific disciplines that potentially, Parthian view introduces, right?
Yeah, it's very nice. On a kind of category of categories.
Right.
Yeah, and you can consider some kind of notion of category of categories in technical way, and it is kind of category as some kind of object and functor or the other kind of mappings between the category. So and this approach is nowadays unified to the study of topos. So a kind of category which can be used to develop category theory or other theory. But the original paper by Lavia on the category of categories is very, how to say, will inspire you in this paper. Philosophically, this is very good paper, even in nowadays, I think. In that sense, every category is in a sense equal. Equal means equal footing. It is, how to say, there is no great category, there is no tiny categories. yeah, it is even if it is tiny, it's kind of the equal footing existence. So my view of the world is very much like this category of categories. So you can project out this some aspects of our world as some category, some aspects as some category. But this is not a discrete one. This is of course related, very rationally related, and sometimes this category is become the dominant role. Sometimes this category should dominant role. Then we don't lose anything in the scientific domain, and also have the flexibility on philosophy also. So how to say, for example, some kind of physicists tend to think that microscopic aspect is the true aspect of the mathematics. Sorry, physicists may not, but more physical-oriented scientists tends to think the microscopic thing is the real aspects of the world, and macroscopic is some kind of illusion or something. But this is not the case. Every level, scale is realistic, and interesting. This kind of level is interestingly can be grasped as some categorical structure, I believe, because of our experience. All scientists must, based on the experience or the structure of experiences. The only one shot experience is not science, but it's the relationship and sameness or differentness of the experience is our basis of sciences. I believe, strongly believe, that our structure of experience is very harmonious with the category theoretical structure. Then our sciences have, if you cut here, every aspects may be how to say, grasp the categorical structure, and then the unifying the sciences is main target of application of category theory.
Yeah. Is there anything, Alex, you wanted to say? Hayato, you may need to leave.
Yeah, I have to go to the meetings in our university.
Is there anything you want to say, Hayato or Alex?
I just wanted to say that was really really interesting, and the last thing was extremely beautiful, and I couldn't agree more. It was nice to meet you, Hayato. Nice. Yeah, it's maybe the very last thing. I think the reason that I got so enamored by all of this is exactly as you said. I think the reason that so many naturalistic thinking scientists believe that it's the particles that's real and everything else is not real is because we seem to have the most rigor, because we have simple equations, by quantum physics and Einstein and Newton. And I think what you are working on is that you're showing you can have the same rigor for these higher levels. So that is exactly that's exactly where this all comes together for me. Then because why else would you think this is an illusion, as you said? It was only because it seemed that we cannot measure it and describe it as well as these particles. Now, it seems that these particles don't exist either, the more we learn about those, right? And so it all comes maybe together in realizing everything is just structure and relations. So, but yeah, I think that's why your work is so important. So thanks very much.
Yeah, thank you. And I'm very excited to have this three people's conversations, discussions. I don't know. We have these discussions until 2 hours ago, but I'm very happy to have this. I think that this discussion will inspire the many kind of people. So thank you now to give this chance.
Yeah, thank you. I think yeah, if I prepare this a little bit more, maybe you guys would have be better prepared, but that's also all right. This kind of that preparation radio style may also work as well. So
very nice.
Yeah.
So I have to go. So see you in very near future. Thank you.
Bye.
Thank you.
Let me
Bye-bye.
stop the
Bye-bye.
recording for now.
Okay.